Hello, viewers of mine. This is a presentation about acceleration. Specifically, we're going to be getting into the big five equations. Woohoo! But first, a little word of acceleration as discussed in The Blues Brothers. Very fantastic movie. Famous lines, a lot of famous lines, including this one. Elwood says, "It's 106 miles to Chicago. We got a full tank of gas, a half a pack of gum." That's in quotations. He doesn't say gum, he says cigarettes. But I'm not supposed to say that in school. It's dark and we're wearing sunglasses. And Jake says, "Hit it." But what he really means is accelerate. Eh? Yeah, physics. Even in the movies, right? So, other ways to calculate acceleration. So, we've been doing a whole bunch of stuff on graphs, but let's see if we can do stuff with equations as well. So, here's our learning target. I can choose the appropriate big five equation to use based on the information given in a word problem. So, think about what we've done so far. We've learned the only equation we've learned so far for acceleration is delta v over delta t. But what if we're not limited to just delta v and delta t? What if we wanted to know about displacement? Yes, what do we do then? Well, we could do graphing. I could take a position time graph and I could take the slope and get velocity. And then I could take my velocity time graph and take the slope and get acceleration. And then I could also work backwards, going from acceleration to change in velocity to displacement. That would be a whole lot of graphing, a whole lot of sloping, a whole lot of area under the curve. It would be so much easier if I could do equations. Graphs are lovely, even when they're being held up by someone that looks kind of like Conan O'Brien. But let's see if we can do it more easily. So we are going to do the big five equations. The following equations may only be used when dealing with constant acceleration, which is what we're going to be doing here. Now, when you take AP Physics C next year or go on to college level physics, you'll learn about situations where acceleration is not constant. And also, actually, we will do a non-constant acceleration later on in this year, uniform circular motion, but we'll talk about different equations by the time we get there. Okay, so here are the big five. So, the big five? Now you might be saying, Fair, what in the world are you showing us here? Well, first of all, does anyone recognize what these are? Okay, they are the big five animals of Africa. So, many years ago, I went to work in Zambia, which is in southern Africa, and I worked with a bunch of physics teachers out there, and it was my job to talk about acceleration. So I was going to show a presentation on the big five. And so when flew into Zambia, the Lusaka airport, that's a funny one. That's a tiny little airport. But anyhow, I get there and I start seeing all these advertisements for the big five. It's like, get the big five on a t-shirt, get the poster of the big five. You can get shot glasses with the big five. And I was like, wow, they take their physics equations very seriously here. And my colleagues were like, no, that's not the physics equations. These are the big five animals of Africa. So, in case you weren't sure, this guy is the lion, the leopard, and actually, the leopard is the only one of these pictures that we didn't take ourselves. Kind of an interesting side note, but yeah, we were able to see all these ourselves in person, which was exciting and also scary. There's the Cape buffalo, elephants, and white rhino, and as you can see, the white rhino is on the road. We were so excited. We were driving along and we saw this rhino coming down the road toward us, and we're like, oh my goodness, stop, let's take pictures. And we're taking all these pictures, and the rhino just kept coming toward us. We're like, that's interesting. So we backed up a little bit. The rhino kept coming toward us. We backed up off the road, and the rhino just kept coming toward us, and we're like, dude, back up more. And the driver, Charlie, was like, oh, I can't. We're like, why not? He's like, because that's the Zambezi River behind us, and it's full of crocodiles. So we're like, oh. And you can see this white car is just kind of pushing the rhino toward us. We're like kind of freaking out. Luckily, the rhino just went past us and kind of snorted on its way. It's saying like, what's up? You know, I don't know. Anyhow, so those are the big five animals of Africa. Let's see the big five acceleration equations for physics. So we have this guy, VVAT. VF is equal to VI plus AT. We have the average velocity equation. D is equal to 1/2 or 0.5 VF plus VI times T. We've got D is equal to VIT plus 1/2 AT squared. We've got the VF squared equation. VF squared is equal to VI squared plus 2 AD. And then finally, and this is the one that you probably won't see very often, you will see, let's see, you'll see this equation and this equation and this equation in almost, I'd say, any physics textbook. About half of them, half of them show this one, but then very, very few will show this one. But you'll understand why I'm showing this to you. And notice this one is very, very similar to this one. It's D is equal to VFT minus 1/2 AT squared. So notice the V final versus V initial, and then there's a minus sign instead of a plus sign. Otherwise, they are the same. So where did these equations come from? Quick, brief overview of that. There's the VVAT equation, and you can see this is actually from the delta velocity equation. Okay, and then it combines with the acceleration is delta V over delta T, and so we can substitute these together, and we get VF is equal to VI plus AT. You can also show this graphically if I have a nice velocity time graph, and I have 2 points on there, initial and final velocity, and I can actually plug in the values, and it does work out showing the physics, so that's cool. Okay, in other words, I can solve for stuff on a graph without actually having to use a graph. I can just use an equation. Then there's the average velocity equation. So using the same graph, I can take the two velocities, add them up, divide by 2. That's how you take an average of something. Okay, and then you can use that in the distance equals rate times time equation, or the equation that we already learned, which was displacement is equal to velocity times time. Except instead of just saying velocity, I'm going to be using the average velocity. And go ahead and plug in and solve, and it does in fact work out. So that's lovely. That's the equation I was just talking about. You plug it in, and you can also solve it graphically. If we want to take the area under the curve of a velocity time graph to get displacement, notice this here is a rectangle, and that's going to be base times height, or length times width. And then this guy here is a triangle, so that's 1/2 base times height. Okay, so color coding there so you can kind of keep track, but you combine those areas together, and that's how you get the displacement. Okay, so cool algebra, but you don't have to worry about actually doing it yourself. And then we're going to take those two equations and then just kind of smush them together and solve for different things to get the other three equations. So here's the 1/2 AT squared equation, combining the two equations like this, subbing in for VF, and then distributing, and then you combine the first and the last parts, and you get D is equal to VIT plus 1/2 AT squared. Now, if there is no initial velocity, which will happen a lot, especially when we're talking about acceleration due to gravity, we just get D is equal to 1/2 AT squared. That's pretty handy. That is certainly not always going to be the case. We can easily have initial velocity, but a lot of times we don't when we're just dropping something. Next equation, VF squared equation. This is the fanciest math rearranging that you'll have. These two equations, once again, rearranging the VVAT equation for t and then substituting into the first equation, you get this messy guy down here. But wait, it gets messier. As you can see, VF plus VI in parentheses times VF minus VI in parentheses. You might be thinking back to your Algebra 1 times and you're like, wait a minute, can't I do FOIL? Why, yes! First outside, inside, last, and you smush all that together, rearrange, and solving for VF squared, you get this guy. Oh yeah. Oh yeah. Good stuff. And then finally, the fifth equation, which doesn't get used very often, but it's still very useful and it's still legit. You, once again, start off with these two equations. You solve and substitute for the VI. Okay, so we are subbing into the blue equation for the VI. And distribute, rearrange, solve. This is very, very similar to how we got the positive 1/2 AT squared equation, and you get this guy here. Now, so many equations, so few problems, right? You wish. Oh, no, 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 no. That's not how it works. Here's the equations, the 5 equations. If you'll notice, there are 5 equations. Duh, just said that. But there are only 4 variables in each equation. So the first one has the 2 velocities, acceleration and time. The second equation has displacement, both velocities and time. The third equation does have 1 velocity, the initial, displacement, acceleration, and time. Notice though what they don't seem to have, and that's going to be very, very important here. They do not have, this first one, the VVAT, does not have D. Okay, so actually I'm going to put that over here. I'm going to make a new list right here. D is not in there. Okay, this guy, acceleration, is not in there in the average velocity equation. This guy does not have V final in it. Okay, this guy does not have T in it. No time. And this last one does not have initial velocity. And I said it's very uncommon that we use this one because most of the time problems just give us initial velocity. Or sometimes we're solving for it, but most of the time we're just giving it. That's just based on the way the problems are set up. Okay, and now we're getting to the point of this. So there are 5 equations. I told you that every textbook will give you 3 of the equations. Some of them, maybe half of them, will give you the 4th equation. So let's see, where are we? Every one gives this guy, and this guy. Half of them give this, and hardly anyone gives that. So you say, Fair, why are you telling us to memorize extra equations? First of all, I'm not going to have you memorize these things. Just write them down, use them, have a list. No problem at all. But the reason I'm having you use 5 equations is because, as I said, there are 5 variables in these acceleration problems. 5 variables. We're only ever going to be given 3 of them. So for example, we might be given, and we'll actually solve some problems in just a moment. We might be given initial velocity, final velocity, acceleration. Will be, so this, and this, will be asked for displacement. And then I won't really care about time. Time is something I won't care about, hypothetically. So you say, well, what equation should I use? Well, let's see. I need an equation with initial velocity in it. So let's see. It could be this first one. It could be the second one. It could be the third one. It could be the 4th one. Oh, it's not this last one. It's not the 5th one. Okay. I need an equation with final velocity in it. All right. It could be this first one. Could be the second one. Oh, it's not this one. It's not the 3rd one. Could be the 4th one. And we already said it's not the 5th one. I need something with acceleration in it. Okay. Gee whiz. It could be this first one. It could, and so on. This is taking a very long time because then I'll have to do this again for displacement. Very time consuming. So what is so much cooler than doing this? So much better than doing this. Instead of saying, I need an equation with this, this, and this, and this, I'm going to say, hey, I don't care about time. So what equation does not incorporate time? Oh, this guy here, VF squared equation. Boom. Nice. Let's try it a different one. Let's see. So I have initial velocity, final velocity, acceleration, displacement. Oh, I ran out of space. And time. So let's say I'm given initial velocity, final velocity. Stop that. I'm not given acceleration, nor do I care about acceleration. I'm given displacement, and I'm asked for time. If I don't care about acceleration, which equation will I use? I'm going to use the equation that doesn't care about acceleration, which is the second one. That's the d is equal to 1/2 vf plus vi t. Nice. Okay. Oh, and this other one over here, this was the VF squared equation, right? VF squared equals VI squared plus 2AD. Ah, very nice. Amaze your friends. Physics. So, hopefully you have figured out the learning target. If you remember, the learning target was, can you choose the appropriate Big Five equation based on the information that you're given. So hopefully you see this is a nice, super efficient way of doing it. Physics.